For the purposes of this problem, we assume the atmosphere is divided into 3 slabs. In each slab, we have calculated the average temperature. There is a satellite up here that is trying to measure the energy from here. This is the amount of energy radiated in the wave frequency nu I that is given by this formula. This comes from radiation physics. You can essentially see R is the energy. This is the channel through which it radiates. T is the temperature. W is a function whose explicit form is known. P is the pressure. Gamma are parameters which are known in radiation physics. So if you assume gamma is equal to 1, this is R of nu 1 is equal to exponential of that is equal to that. And then this integration is through the whole depth of the atmosphere. But in our model, the temperature is not uniform across the depth. So I have to split this integral into 3 parts. 0 to 0.2, 0.2 to 0.5, 0.5 to 1. So if you integrate this, you know the explicit forms. All of you with me? What's going on in here? So you have the energy radiated as measured by the satellite in channel nu 1 is equal to given by this quantity. So what is H1 of nu 1? That is this integral, because T3 gets out, T2 gets out, T1 gets out. You integrate that, and these are all constants. So if you repeat this for the 3 channels, how many heard me? So there are 3 temperature measurements. Our idea is to be able to recover the temperature. So I'm doing what's called a twin experiment. So what are we going to do? We are going to assume the temperature is known. I don't have satellite data in here. So I'm going to simulate the satellite data. So I'm going to assume the temperature to be known. I know the radiation formula. I'm going to first compute these radiated energy. Then I forget the T1, T2, T3 that led to this. I start with these measurements. I calculated this perfectly. In practice, nothing is perfect. You have to add noise. So I add some noise to this, some noise to this, some noise to this. That constituted my observation Z1, Z2, Z3. So this right-hand side is linear relation, linear relation. So before I go further, that's what we talk about in here. Generate H nu I for 5 channels by adding noise. Add the noise Vi to first generate this deterministically. Add the create the noisy observation. This can be rewritten as Z is equal to H of X. My X is the unknown vector T1, T2, T3. Why X is unknown? Because I calculated the R's, I have added noise, and I have forgotten the T's that gave rise to this. So I'm pretending I have an actual satellite data observation. This kinds of simulating the observation in meteorological community is called twin experiment. You take the model, generate the solution, add noise to this, create observations, and store the value of the parameters initial condition that led to the observation someplace safe. Then you have a noisy observation, set up the model, try to retrieve the parameters of interest to you. Then you have the original one that you have hidden. You can compare the two, and then you can benchmark the quality of your methodology by using these kinds of experimentation. This is how you sell your product. All of it, me? That's right. So compute, this is a linear model, compute the estimate, compute the error as a function of the noise variance. So one of the standard exercises in my classes that I would like to ask them to be able to plot the norm of the error as a function of the noise variance, and so on. You can generate different kinds of experimentations. Are you with me? So this is a very simple problem that has a physical relevance that also tries to illustrate the linear least square problem. It's a temperature retrieval problem. In Wisconsin, University of Wisconsin-Madison, they have a center which is totally dedicated to retrieving temperatures at various layers from the actual data measurements. This is what they do. This is what they have been doing for the past 2 decades. There are specialists who spend their life in trying to fine-tune algorithm to be able to recover temperatures using satellite measurements. So this is the twinkle twinkle little star, as I used to say, in a game, to be able to see how these things can be applied. So this is the linear problem. Now this is not what you are going to be working on. What you are going to be working on is a nonlinear problem. We are going to change the problem slightly. Change the problem slightly. Here again, I have divided the atmosphere into 3 regions: 0 to 0.25, it will be 0.25 to 0.5. Oh, I'm sorry. I'm sorry. Okay. Here, in the earlier case, I talked about regions that are disjoint. Now I'm going to be talking about regions that are slightly overlapping. So I'm going to be talking about 0 to 0.25, then 0.2 to 0.5, then 0.3 to 0.7, 0.6 to 0.8. Do you see the overlap? Yeah. Average values in different slabs. Yeah, but then that all comes from the radiation physics, which I don't know too much about. So this is the first approximation to what you do. The temperature actually varies continuously, right? So in order to be able to model, you have to slab it and then make some approximations. Okay, good. So the data that is given to us, so this is the data that is given to us. The amount of energy radiated from this segment of the depth is equal to 0.21. How many heard me? This is actual measured from here, actual measured, from here actual measured, from here actual measured. The temperature itself as a function of pressure is a quadratic function. It has 3 parameters, x1, x2, x3. P varies from 0 to 1, atmospheric pressure. So we postulate that the temperature varies quadratically with 3 parameters using this quadratic function. Zij, which is given here, is the integral from pi to pj of Tp dp. Tp is given here, pi pj. So what does it mean? Z1, if you call this 1, if you call this 2, this is Z12. Z12 is equal to integral 0 to 0.25 of this Tp. So if you plug this in and integrate this with respect to P, this will be a function of x1, x2, x3. Nonlinear in x1, x2, x3. How many of you have made? Come on, guys. So the left-hand side is known. The right-hand side is a function of the parameters. It becomes a nonlinear because x2 occurs as a square. So it's a nonlinear parameter problem. So again, if I is 3, j is 4, if you integrate this from 0.2 to 0.5, this value is 1.5. If you substitute this, you will get another nonlinear relation. How many of you may? So you will have 4 nonlinear relations. So I'm just trying to illustrate the first one. Z12 is equal to 0 to 0.25 of this, which you do like this, you get this. This is called H1x. You remember our standard problem? Z is equal to h of x, z1, z2, zm, which is equal to h1 of x, h2 of x, hm of x. X itself is a parameter, x1, x2, xn. This is a standard problem. In this case, m is equal to 3. In this case, m is equal to 4. 1, 2, 3, 4. So I have 4 nonlinear relations in 3 unknowns. Apply the nonlinear least square technique, retrieve x1, x2, x3. How many of you have an aha understatement of the problem? Your problem well understood is half done. right? Okay, good. So only a very few population raise the hand. I know after dinner, after a heavy lunch on a hot, warm, humid day, it's not easy. I understand that. But Amit says we have to do it. Exactly. Are you with me? So this is h1 of x. Can you compute this? This is the number. Can you compute this? This is a number. Can you compute this is a number? Then you compute this is a number. So what is this? It's a quadratic function. So each of the hi's are quadratic functions. These coefficients will vary because the limits vary. Are you with me? So I have 4 equations in 3 unknowns, nonlinear. Here you don't have to add noise and such thing. So this is already a noisy observation. So you have, so in this particular case, you simply have h1 of x is equal to z1, h2 of x is equal to z2, h3 of x is equal to z3, h4 of x is equal to z4. Are they? Recover x. So what is that you need to do? You need to set up. Am I supposed to tell this on it or? Okay. I anyway started it. So this is the function you have to minimize. So find an x that minimizes that. So how long we are going to give time in terms of time? Or should I talk about the next problem also now?
Yeah, I think so.
Okay, good. Okay, good. We are going to be talking about 2 problems so that we can let you loose. You don't have to do it when anybody is watching you. You can go any place. So this is the first problem. Are there any questions on the definition of the first problem, the statement of the first problem? Okay, the previous version I talked about is the linear version. Let me quickly show you that for the sake of illustration. So energy radiated is given by this. So radiation physics people, different people have different beliefs, different formulas come in because there is cloud cover, there is no cloud cover, so there are lots of different variations. So if you look at the expressions for the energy radiated from various slabs of the atmosphere in various frequency ranges, there are extremely complex, complicated expressions. So this is the pathway into those complex world, but so this is how we have to walk through. So this is a very simple way to emulate what they do in Wisconsin at the Satellite Research Center. Okay? Questions? Good. Silence implies consent. I'm now going to go to the next problem. The next problem is about interpolation. You remember we all talked about the H matrix observations. Now I'm going to tell you a very simple case where H comes out of essentially an interpolation scheme. So let me, it's again from chapter 18. Yeah. I have problem 2. So consider a domain It's a 4x5 grid. There are 20 grid points. Let us assume this is part of Yelaganka, a square domain around the bus stand in Yelaganka. I have measured the temperature, let us say Z1. I have measured the temperature, say Z2. I have measured the temperature Z3. So let us say I have measured the temperature Z4. Let's assume I have measured the temperature Z5. Are me? I have measured temperature at 5 locations which are distributed like this. So what is the distribution? In each grid box, there is at most 1 observation. Some grid boxes have none, some grid boxes are there. And let us assume these are all temperature. So there is no conversion needed. What did we say essentially in meteorological problem? I have a model space, I have an observation space. So in this case, the model space n is equal to 20. In this case, observation space is equal to 5. I have 5 observations, 20 state variables. I would both are temperature, and we talk about the relation H. So H is essentially an operator that mirrors the temperature at a point 2 over the grid points. If you think it will be helpful, good. Majority has it. Okay. So if I have, suppose this is the unit interval. This is the unit interval xi plus 1. Or let me talk about a 1D problem before I come there. Suppose I have a domain like this. 1, 2, 3, 4, 5, 6. I have observations in here. I have observations in here. It's a 1D version of this 2D problem. So what do I want? I would like to be able to relate. So I have x1, x2, x3, x4, x5, x6. I would like to be able to relate x2, x3 with z1. So what do? I would like this is my z1. I would like this to be my x1. I would like this to be my x2. I'm going to draw a line. I'm sorry, my line is not screwed up. Okay. Let us assume the grid length is unity. So let me assume this length is A. This is 1 minus A. So I'm going to do a univariate interpolation. Then you can do a bivariate interpolation by applying this twice. That could be a nice exercise. Okay, so how do I interpolate this? I would like to make sure the slope is the same. So what does that relation tell you? z1 minus x1 by a must be equal to x2 minus z1 by 1 minus a. So instead of 1 minus a, I don't have to write too much. I'll simply b. A plus b is 1. So I would like to be able to express x1 and x2 in terms of z1 and a. So how do we do that? A z1 minus, b z1 minus b x1 is equal to a x2 minus a z1. Bring all the x1, x2 to one side, the other side. So that gives rise to b x1 plus a x2 is equal to a z1 plus b z2. A z1 plus b is z1. A plus b is 1. That is equal to z1. How many follow me? Come on, guys. So if there is one observation here, so if this length is a, if this length is b, b times x2 plus a times x3 is equal to 0. That's how. How many follow me? So how many such relations I have? I have only 2 observations. So my H matrix will have 2 rows. How many columns? 6 columns. So how is my H matrix going to look like? Z1, Z2 is equal to 1, 2, 3, 4, 5, 6. This is x1, x2, x3, x4, x5, x6. Okay, Z1 is affecting only 2 and 3. So this is 0, this is 0, this is 0, this is 0. Everybody? Z2 is affecting 4 and 5. So this is 0, this is 0, this is 0, this is 0. How many follow me? I don't see too many nodding heads. That's right. So in order to apply this rule, what is that I now need to know? I now need to know the following. What is the distance of Z1 from its left boundary? Call this A1. Call this B1. A1 plus B1 is equal to 1. Well, the distance of Z2 from this, call this A2. Call this B2. A2 plus B2 is equal to 1. In other words, in each domain, the observations need not be located at the same. So A1, A2 are the two parameters. So once you know A1 and A2, you are done. Okay, so from this formula, what do I get? B1, A1, B2, A2. How many of you have an aha here? Z is equal to Hx. So this is 2 by 1, this is 2 by 6, this is 6 by 1. I am given Z, I know H, find X's. So in this case, M is less than N. There's an underdetermined problem. That's exactly what Amit wanted me to talk about. We want to give an example of an underdetermined problem that comes very naturally. Amit, with me? Okay, so what is that now you need to do? One or two clues. Is the 1D problem clear enough now? If the 1D problem is clear enough, so what is that you need to do? This is a homework problem for you. So this is, let us assume this is xi, this is xi plus 1. So in here, you have to compute the following. What is the number of grid points in here? 4. So if I consider this I, this will be I plus 4. How many for me? Come on guys, there are n points. So if this is this, that, this is I plus 4, this is I plus 5. Because x is equal to x1 to x20, we need to be able to ascertain which of the x's will be affected by the z. The z affects only those guys who are in the corner. That's an assumption. Are these the only guys who is affected? Can these guys be affected? You have different algorithms. So if you get one idea and have an aha, you can do anything in life. Are you with me? So the z1 is going to be affecting x6, x7, x10, x11. So first what do you do? So here is z1. So you first need to be able to find the distance z1. So this distance I would like to call it a1. This is b1. I would like to call this distance a2. I would like to call this distance b2. Don't confuse this a2 b2 with this a2 b2. A1 is the horizontal distance or the horizontal coordinate of z1 with respect to xi as the origin. A2 is the vertical coordinate of z1 with respect to xi as the origin. Local coordinate, local measurements. Are you with me? So what is it first you need to do? You take z1, interpolate it to these, z1 bar and z2 bar. Can I interpolate this to these two using a1, b1 by this formula? How many of you know? And then once you interpolate this is a2, this is b2, then you can pull this place. You can pull this place. So you first pull it to this way, pull it to this way, pull it to this way, so this guy goes to all the 4 places. Therefore, in this relation, what is it you will get? You will get, can I raise this part now? How many of you are with me? So in our relation, what is it you will get? You will get, in this particular case, z is equal to z1, z2, z3, z4, z5, right? That's right. So this matrix is going to be 1, 2, 3, 4, 5. What is the number of columns? 1 to 20. And the x is going to be 1 to 20. How many heard me? You can partition this like very easily to be able to help you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 19, 18, 20. You can partition this. How many heard me? Now that we know this in here, x6, x7 is not 0. x10, x11 is not 0. Everybody else in that row is 0. How many heard me? Fill in, fill in, fill in. So what is the matrix you are going to get? You are going to get a 5 by 20 matrix. What is the formula for the retrieval? The retrieval x hat is equal to H transpose inverse Z. That's for the underdetermined system. How many of you remember that? For the overdetermined system, if you remember, this is for overdetermined, this is for underdetermined. Our problem is underdetermined. So set up this matrix. Okay, so what are the various things you need to do? You need to assume this distance, 0.5, 0.5, 0.3, 0.7, 0.2, 0.3. You have to locate this randomly. If every one of you this is independently, there is no reason two people should get the same matrix, right? Come on, guys. So don't wait for your neighbor to do it. You do it.
So we can locate it equally also?
But don't put it all the time equally to make your life simple. That's right. That's right. It will not be all the time equal. You could, you want to do that. Yeah. Computationally, whether it is 0.5 or 0.3, doesn't make much difference. Yeah, I'm sorry. Choose random numbers. That's right. So in other words, there are two random numbers you need. What are those? You need to be able to get each coordinate from here. So there is a horizontal coordinate, there is a vertical coordinate. So you need to choose two random numbers, A1, A2. So AI is in between 0 and 1, or strictly between 0 and 1. Yeah, right. What is the probability of getting 10 point numbers, 0.5, 0.5, 0.5, 0.5? You know the probability? Okay, it's very slow, right? That's right. Are you with me? Okay, good. Now you may wonder, what is Z you want me to give? You pick your Z's randomly. Everything is random here. In other words, but don't pick it too randomly. If you consider a 20 meter by 20 meter area around the bus stand Yelahanka, does the temperature vary too much? So when you randomly generate it, if the temperature is too different, then that's not Yelahanka, that's somewhere else. So your Z's are not going to be too different. Are you with me? Suppose you have a thermometer under the shade. Suppose you have a thermometer under the sun. So there will be some difference. In other words, you can think there is an average value, and there's a perturbation of the average value that gives you the Z's. So choose Z's to be the temperature of Yelahanka on Friday, July 8th at 12 o'clock. That is Z. Look at put the grid in Yelahanka. Temperature location. Set up the problem, then compute the temperature at every point where I did not have an observation. That's the retrieval problem. Alpha, the problem clear enough? How much time do you want to give? When do you want to meet? We are going to, okay, because when does the coffee break start? 4.
And then after that is a
question session. For question session, I'm expecting some more question because where is the SVD guy? Right here. Where is the Podivar guy? That's here. There are a few people who wanted to ask several questions. They have been asking in the background, so I thought if you bring that question to the foreground, many people may have aha too. So
solutions to these problems before the
okay. Enjoy. We will see you soon. You want to add anything?
Maybe it's not part of the doing, but the projects in the last week. So the idea would be have something like
xi plus 1 because a2 times xi plus k plus 1 is equal to c to loss. Okay? Then, don't die. So, what is next? Substitute, that's correct. Once you substitute, what the formula you get, come on, write it down. Come on. So what is the row I need? I need the row like this, right? Here is xi, here is xi plus 1, here is xi plus k, here is xi plus k plus 1. This is 1, 2, Okay. Everywhere else will be 0. This will be non-zero. This will be non-zero. This will be non-zero. Non-zero. Everywhere else will be 0. Come in. See, fill this. If you have a notebook, you have answer, you can come. Hey, don't go, stay here. A prime, call it B prime. A prime plus A plus A prime, 1, B plus C prime, 1. Okay, so this is the H matrix. H is partitioned into 4 blocks. And H1 is here, H2 is here, H3 is here. You put all the things together. And what are the elements? A1, B1, this one prime, B1, A1, B1 prime, A1 prime, B1 prime. If you add all these things, you get 1. Somebody will make. Okay, that's what I'm talking about. You got that? I give you that. So in this particular case, I is 2, 3. So it all depends on where the location is, where the specific thing is, right? The I depends on the square that contains all the So that's what I said. You do this and repeat this every day. So this is the stencil. Move it up.
The idea is that if you want to calculate this thing.
Oh, good. He's explaining. I'm glad. I'm sorry. Go ahead.
A, B, C, D. This is also A, B. This is also C. So when you are writing this matrix, so for this example, so you have this point. X1, X2, X3, and X4. So when you are writing for this, what will be the coefficient? B into D. You give up this B and D. So BD will come. And there are A1 and B1. So here BD. So let's take it. Now when you are writing coefficient for this, you just show these two. So you have A and D. So the coefficient will be okay. So that way you find out coefficient for this. So x1, x2, x3, x4. So this is x7. So for x7, you will get this two, A into D.
Can I do something? You don't have to do it for each one. You can essentially assume the general thing. So that's what I ultimately would like you to think about. If you have 2 points in here, they differ by 1. Then this point and this point index will differ by the number of points here. So that the number of points the x-axis will be k. So if this is xi, he must be xi plus 1. He must be xi plus k. He must be xi plus k plus 1. Okay? I would like you to think in terms of this general module. If you understand this module, then you simply you take this module in here, 3, 4, 7, 8. If you take this module and put here 11, 12, 15, 16. If you take this in here, 9, 10, 13, 14. You don't have to repeat doing this. You have to do this once. And then apply this again. So that's the stencil. You develop that stencil and carry it around. For each observation in the row, and what is the, when do you know your calculations are right? Your row sum must be 1. Are you with me? Everybody have an eye here? That's how you check that. And then this matrix is a sparse matrix. It has more zeros than non-zeros. So to multiply HH transpose, you don't need a computer. There are just too many zeros. You can compute that product by carefully writing this down very quickly. So once you HH transpose your computer, you can compute the discourse solution. You can use normal equation methods, mathematics. That you cannot solve by hand, 4 by 4. I don't think it will be. Yeah, I don't want you to waste your time in solving a 4 by 4 system. That we can use. How many of you are with me? Is this interpolation problem done? If you don't do it now, I would like you to at least finish this, but then Amit, you have to answer Amit, not me. At least conceptually you are done. So I would like you to write the matrix and have that ready and do that. And how many of you have made progress in the radiation problem? Very good. I'll go back to radiation problem.
Okay, so Jaman.
To get the form of H1, H2, H3, H4. So you have 4 observations, M is 4, N, the number of parameters 3, Z is equal to H of X. H of X is a nonlinear function of the parameters. It's a nonlinear estimation problem. Get me? You have been given a current operating point. So you need to be able, you should be able to linearize it around the current operating point. So in a small neighborhood around the current operating point, you replace the original by the first order linear approximation. Then convert it into a quadratic minimization problem. You solve the quadratic minimization problem by solving the 3x3 system. How many of you with me? Compute the correction. Add to the original. You move to a new operating point. Repeat the show. Repeat the show. Repeat the show. Until such time that the increment that you are going to be computing is very small in magnitude. Very small compared to the current value. All of it, me? That's a convergence criteria.
Request you to write one step, like one operator.
Okay. You have xc, you have j of x is equal to 1/2 of z minus h of x transpose z minus h of x. You have to replace h of x by h of xc plus dh xc times x minus xc. You substitute this in here. You substitute this in here. Everybody in place? Okay. How many of you can take it from here? Right? Then, if you substitute this in here, what do you get? You get j of x is roughly equal to, because I'm going to approximate 1/2 of z minus h of xc minus dh xc times x minus xc transpose z minus h of xc minus dh of xc by x minus xc. We are going to call this g. We are going to call this g. So this is equal to 1 g minus dh xc times x minus xc transpose g minus dh xc times x minus xc. This is the quadratic function, so I'm going to call it first order quadratic approximation. You compute the gradient of q1 of x equated to 0. How many of you with me? So what is the relation you get? The gradient equation, when you do this, xc dh xc x minus xc must be equal to dh transpose xcg. Yeah, that is the equation that you must get when you compute the gradient of this first order approximation to 0. How many of you are with me? So given h, compute the Jacobian, evaluate the Jacobian, compute this matrix. X minus xc is given by that. So g is equal to x minus, everything is known. So what is dh? dh is equal to is a 4x3 matrix. So dh transpose dh is equal to is a 3x3 matrix. You compute this, what is that you get? You get the solution x minus xe. So what is the new operating point? The xc new is equal to I originally started with XC, plus I got the correction x minus XE, these two gets cancelled, is equal to X. That means you compute this X, and that will be the new operating point. That's the first loop. I'm going to repeat the whole show. Repeating the whole show is very easy because you already have calculated the Jacobian. You simply need to keep evaluating the matrices and keep going. How many of you are with me? How many of you have finished this? I know several people have finished this. Can you finish this now? We can. I know many of you may be new to Bangalore. I don't want you to be working too hard. Go around, see Bangalore. But when you get bored seeing Bangalore, finish the problem through. Now, stopping criterion. There are a number of ways of doing this. If x minus xc absolute value is less than 10 to the power of minus d. So what does it mean? This is the absolute value of the increment, right? The absolute value of the increment is a fraction. It could be 10 to the power of minus 4, 10 to the power of minus 3, so on. If you write the program, you can, by changing this convergence criteria, you can get results of various accuracies. With me? How many of you are with me? Good. Are we done? Are we good to go? Good. Now let's, the other problem with respect to interpolation, our friend has already solved it. Did you solve that? Yeah. Is there any question on that? Yeah. No, one by one. Which question? On which problem are you asking question? Huh? Interpolation.
There is essentially A plus equal to 1 always.
Well, look at this now. I'm assuming that, yes, it's always 1. I am assuming the grid length is 1. So I'm going to be putting an observation here. So if this is A, if this is B, A plus B must be 1.
For example, like this is 10 kilometers.
What?
10 kilometers.
Okay. Then if it is 10 kilometers, A plus B will be 10. I'm assuming this is 1. Per unit basis, buddy. Are you with me? Yeah. Grid length is 1. So when you say xk plus 1 is equal to f of xk, what is 1? The one time period, delta t. Is delta t 1 minute, 1 second, 1 day, 6 months? It could be anything, right? So we simply call it delta t. So like that, in here I'm assuming this is 1. If this is 1, A plus B must be 1. So if this is 10, A plus B must be 10. Are you with me now? Any other question on that, please? Are we done on both the problems? I believe you should finish both of them, complete them, and have an aha. You should not leave Bangalore until and unless you solve this problem and have an aha. How about that? Come on, guys. If you have questions, the best time would be to interact with people who do it. That way you have an aha. Good. So with that behind us, now let us go back to other topics that you wanted to ask questions but didn't think of it or didn't want to ask at that time. So let us open up the floor. Could you, sir, hello? You can stop this. We are done with this. You can pull this up too. But oh, you want to do SVD? Okay. You remember that DARP problem you did? You all know the algorithm. You want to know what makes that SVD algorithm work. So I'm going to quickly talk about the SVD algorithm. Good. Let us suppose I'm going to work in terms of the matrix H. H belongs to m by n. Given H belongs to m by n, I can create two sets of matrices, and let us assume m is greater than n, without loss of generality to start with. I am going to define what's called Gramian matrices. Gramian matrices. Given a rectangular matrix, there are two Gramians. One is H transpose H, another is H transpose. H transpose H belonging to R n by n. This belongs to R m by m. M is greater than N. By definition, H transpose H is a symmetric matrix. H transpose is also a symmetric matrix. I'm going to assume my H is of maximal rank. Because M is greater than N. Do you all see all the assumptions now? H is a rectangular matrix, full rank, more rows than the number of columns. The rank is equal to the number of columns. I can think of two gramians. So this is one gramian, this is another gramian. Now I'm going to do what is called the eigenvalue decomposition of this symmetric matrix. It is not only a symmetric matrix, this matrix is a symmetric matrix. It is also positively definite. This is symmetric, but this is only positive semi-definite. What is a good way to think about it now? In a positive definite matrix, all the eigenvalues are positive. In a positive semi-definite matrices, some eigenvalues could be 0, rest of them could be positive. Do you see that? Here, 0 as an eigenvalue is allowed, rest of them are positive. Here, 0 is not allowed. Every eigenvalue is positive. So this is the first information we do. So what is the first step? I'm going to do what's called an eigen decomposition of a symmetric positive definite matrix. So what is it we know already? So let me do some little bit of side work and then come back here. Given A SPD, we can do what's called eigenvector decomposition. What does it say? A VI is equal to lambda I VI, 1 less than I less than N. Where VI is called the eigenvector, lambda I is called the eigenvalue. We also know the n by n matrix has n eigenvalues. If I know a priori the matrix is symmetric, the eigenvalues are real. Let me go back. Eigenvalues of a matrix are obtained as a solutions of the characteristic equation. How many of you with me? The determinant of a minus lambda I must be 0. This is a polynomial equation. Roots of polynomial with real coefficients, because elements of A are real. Roots of polynomial with real coefficients can be either real or complex. The real roots can be either positive or negative. It could be multiple. The complex root must always occur in conjugate pairs. All of it? So the eigenvalues lie in the complex plane. So if the matrix is general, the eigenvalues can lie anywhere in the complex plane. If A is symmetric, eigenvalues are real. So that's a structural concern. If A is an addition, symmetric and positive definite, the eigenvalues are real and positive. Okay? Each of the statement is a theorem in linear algebra. You have to prove. I am assuming that you will follow it up later with detailed proofs. The statement that prove that the eigenvalues of a symmetric matrix are real is non-trivial. Okay? Good. So, an nth degree polynomial has n roots. The n roots are the eigenvalues. The eigenvalues have a corresponding eigenvectors. If the matrix has SPD, the eigenvalues are positive. In addition, the eigenvectors also have a very nice and a special relation. But before I talk about that, let me succinctly represent these n equations into one equation. So this is A V1, V2, Vn is equal to V1, V2, Vn, lambda 1, lambda 2, lambda n. You can multiply this and then check it. So I'm going to call this matrix as V. I'm going to call this matrix as V. I'm going to call this matrix as lambda. So I have this relation, n relation, written as one single relation, which is equal to AV is equal to is equal to V lambda. So what is V? V is the matrix of eigenvectors. The first column is the first eigenvector corresponding to the first eigenvalue lambda 1. The second column is the second eigenvector corresponding to the second eigenvalue lambda 2. So V is a n by n matrix. How many of you are with me? That's right. So the fact that A is a SPD tells you lambda i's are positive. And one more, the columns of V are orthogonal. With a loss of generality, I can also assume it is orthonormal. So the V transpose is equal to V transpose V is equal to I. All these things come all together from the property, namely the matrix A is symmetric and positive definite. All of it? So this is called, okay, good. Now I can multiply both sides by V transpose is equal to V lambda V transpose. This is identity. Excuse me. Hey, this is called eigenvalue decomposition. This can also be written as summation lambda I Vi transpose I is equal to 1 to n. So what does it mean? Given the fact A is a real symmetric positive definite matrix, I'm able to express as the product of three terms. V, the matrix of orthonormal eigenvectors of A, lambda, the diagonal matrix of eigenvalues of A, V transpose, the transpose of that. This is one of the most fundamental results relating to symmetric matrices, which as a result this is used repeatedly in many different guises. So this is called eigendecomposition. That's fundamental. That comes from linear algebra. Now I'm going to borrow that result to my Gramian. So given H, there are two Gramians. This Gramian is n by n. This Gramian is non-singular, but this Gramian is singular. All of it, my please? This is m by n. M is assuming greater than n. So what I'm going to do, I'm going to carry the study of the properties of the better behaved Gramian. The SPD, this is a SPD, this is not. So if I apply that, given H transpose H, because this is an SPD, that is symmetric comes naturally, PD comes from the fact this is, the rank is n, there exists an eigenvector matrix, this. So from now on, you forget about this, I'm using the same V here, I hope there is no confusion. Are you with me? So V, can I erase this part? So from the matrix eigenvalue decomposition theorem for SPD matrices, this results exist. So to do this, I should know that. I'm simply applying that.
Do we have to normalize it?
What that? What do you mean a normalizer? Okay, a vector. So when you compute, how many of you have done eigenvalue, eigenvector computation, pencil paper? Good. When you compute a vector, it's enough if you compute a unit vector. Are you with me? Therefore, where the unit vector is normalized. So when you compute the eigenvectors, you always compute a unit vector. In this particular case, the set of unit eigenvectors you compute also happen to be normal, that is induced by the properties of SPD. That's one of the most fundamental and enduring theorems in linear algebra. Now, given the eigenvalues and eigenvectors of H transpose H, I would like to understand what are the eigenvalues and eigenvectors of this. It is there I'm going to be able to introduce some things. Can I have the book, please? I don't think I remember everything, and I don't want to make a mistake, so whenever I need to, I will look at the right page. So now what do? I'm now going to do, so this is the first topic. The second topic, I'm going to analyze the eigenstructure of H transpose. To that end, I'm going to introduce the vector UI. UI be square root of lambda I H of Vi. That's correct. 1 less than I less than n. How many heard me? Now, what is it I'm now going to show? This UI is a transformation of the VI by H. But please understand, VI is the eigenvector of H transpose H. Now I'm trying to do a linear transformation of VI and scale it up. Now consider H transpose UI. So I simply concocted this quantity and trying to do a mischief. I'm going to end up in a very nice result. So it's a useful mischief to do. So what is UI? UI is equal to H transpose 1 over lambda I, H VI is equal to 1 over square root of lambda I, H transpose H VI. Matrix product is associative. How many heard me? Okay, what is associativity? I will give an example. Suppose you go to your departmental store, you have a cart. You buy everything, put it in here, and you put them all in a belt. And in the departmental store, they are very clever people. Only on that way where they have put all the magazines, right? They want to sell you. So what do? You put all the things, the clerk puts it in, you just want to scan all the things, right? Come on guys, what does it mean? You don't care the order in which the secretary or the person at the cashier are counting things. Why? So long as the machine doesn't make an error, the order in which you compute is not going to affect the sum. Think for a moment. Addition is not associative. Suppose you buy 10 items. If addition is not associative, the order in which you add 10 numbers will decide the sum. You have to do an optimization problem. What order I should feed the produce such that the sum is minimum? Are you with me? We'll all still be shopping. We won't come home. Are you with me? That's the power of associativity. So long as you don't mistake in calculations, the order in which you compute is of no consequence. So, associativity, I can change the order. H transpose H VI. Are you with me? But what is this? That's eigenvalues. So I could have rewritten this as H transpose H VI is equal to lambda I VI. Okay, this is the component form, this is the matrix form. Everybody in the place? So this is equal to 1 over square root of lambda I, H transpose. So H transpose VI must be equal to lambda I VI. So lambda I VI. The lambda, so this will be square root of lambda I, H VI. All of you with me? I'm sorry. I should have said the following. I just want to make sure I'm getting the right one. That's correct. That's correct. So, but what is this? This is essentially, so from here, HVI is equal to square root of lambda I UI. So this is equal to lambda I UI. So I'm going to use this formula in here. So what that I have now shown, H transpose UI is equal to lambda I UI, then this is true. How many of me? So I have shown that if VI's are the eigenvectors of the Gramian H transpose H, and if UI is concocted like this, the UI happens to be the eigenvector corresponding to lambda I. So what does this mean? Both the Gramians share the same eigenvalues. This is the n-by-n matrix. This has n non-zero eigen. This has m eigenvalues. M is larger than n. So the rest of the m minus n eigenvalues are 0 here. So they share the same non-zero eigenvalue. The eigenvectors are related by linear transformation. How many have heard me? So that's the first. Now I'm going to concentrate on this one. Everybody? So UI, so how can I write this? UI square root of lambda I will change the sign. This is H of Vi. So let me call this relation as star. Star can be rewritten like this. How many of you know? And how many such relations are there? There is one for each I. Therefore, I should be able to write that H V1 V2 Vn is equal to U1 U2 Un lambda 1 lambda 2 lambda n. So this matrix I'm going to call lambda to the power half, because the square root of a diagonal matrix is simply square root of the diagonal entries. So this is the matrix V, this is the new matrix U, V is n by n. Amit has been talking about this when he talked about that. So let's compute the size of this. H is m by n, this is n by 1, so this is m by 1. UIs are m vectors, so this belongs to R mn, this belongs to R mn. Everybody? Therefore, HV is equal to U lambda to the power half. How many of you have an aha here? Where did I ask the question? Are you with me?
Yes.
Good. So multiply both sides by V transpose. This is I. H is equal to U lambda to the power half. V transpose. This is called SVD. What is the difference between what Amit said in here? Instead of lambda, he assumed, in his case, lambda I is equal to SI squared. So square root of lambda I was SI. Are you with me? So that is simply a notation. One by one. How many of you are with me? So the SIs, you remember for the dot problem? The SIs are my square root of lambda. The square root is well defined because lambdas are all positive. Why lambdas are all positive? Because my H is a full rank matrix. H transpose H is an SPD. So this is the matrix. Okay, what is this? This is a decomposition. Now let's talk about for a few minutes now. A SPD V lambda V transpose. This is called eigen decomposition. In this case, A is a square matrix. Now what I have done? Using this, I am able to express a non-square matrix to be V lambda to the power half. I'm sorry, the other way, sorry. U this is called SVD. So, eigen decomposition is a multiplicative decomposition. Singular value decomposition is again a multiplicative decomposition. As far as I know, eigen decompositions have been known for a long time. Singular value decomposition, I think, was introduced by physicists. Actually, it was introduced by physicists in the early 30s. There is a name someplace in my book someplace. We can give some of the early. It was a physicist who discovered the SVD to analyze problems. Yes.
So this kind of SVD decomposition is only possible if H is a full rank.
That's right. If H is not a full rank, what is going to happen? There will be less number of zeros. I'm sorry. The less number of non-zero eigenvalues lambda. Are you with me? Same thing in the case of generalized inverse. Remember? That's right. I assumed to be full rank. So first you do for a full rank case, you have an aha, and then ask about, hey, what if? Then if it is not full rank, what does it mean? I can extract the number of linearly independent columns of this, right? You can drop the rest of it. Then it becomes a full rank matrix of a reduced rank. So in principle, there is no loss of generality in doing that. Are you with me? Are you in the money now? Good. What's the next question? Yeah, please go ahead. Comment.
It's not necessary that H is full. The proof that is used here shows that it's true for a full rank.
That's right.
Generally, it looks like it.
Yeah.
That's not.
That's right. But then I wanted to make it very crisp. So that's why we assume default rank and other things. Yeah, thank you. Are we done? Are we good on this? What's the next question? Yeah.
In particular, all the lambda here, zero,
Yeah, okay.
have h which is not.
Okay.
That is the number of zeros they have is exactly the type of matrix minus.
That is right. That is right. That is right. Okay, I want to do one more thing. Maybe Amit will like this too. So this h can be expressed as lambda I to the power half ui vi transpose I is equal to 1 to n. So if I computed lambda 1 is greater than lambda 2 is greater than lambda n. If h is a data matrix, in some sense this refers to a correlation matrix. You remember the notion of lambda as being variance and other things came about? So this represents a correlation matrix. So if this is a correlation matrix, in cases where H transpose is a correlation matrix, the trace of the correlation matrix is equal to the sum of all the eigenvalues that is equal to the total variance. It is in that context the eigenvalues denoting the variance comes into play. And if you order this, so whether you can ask, find a case such that summation lambda I is equal to 1 to k divided by summation I is equal to 1 to n lambda I is equal to 90%. All with me? You saw the 80% dog. You saw the 50% dog, didn't you? Come on, guys. So how did Amit explain that? You are going to set the n minus k eigenvalues to 0. If you set the n minus k eigenvalues to 0, n is given, what is k? I'm going to pick a case such that the k chosen eigenvalues represent 90% of the overall, 50% of the overall, 45% of the overall. Okay, how many of you have heard the name principal component analysis in data mining? It has the roots here. How many of you have heard the term data reduction? It has origins in this mathematical enterprise. So data reduction, principal component analysis, SVD, these are all related concepts. So what is that in the image he was talking about? So think of it like this: there is an object taking pictures as it goes. It says there's a picture of it takes some pictures. The pictures have a large number of bits. So what do? Well, they do some transformation so as to be able to efficiently transmit that. So you need to have onboard algorithms to be able to compress the images. Reduction is an extreme form of compression. So certain compressions are lossless compression, certain compressions are lossy compression. You can go in for a lossy compression with respect to images so long as you don't lose much of the details. So the dog, we were able to get a good picture of the dog with 50%, didn't we? 50 you didn't get it? I forget. Okay, that's right. That's right. So that's reduction. Are you with me? So this idea from matrix theory is applied in several different ways in several different disciplines with different guises: SVD, PCA, principal component analysis, data reduction. So that's the case. Are we good to go? Good. Other questions, please. Okay.
We can use scale decomposition also.
To do what?
To reduce the
No. No. Cholesky decomposition, the idea is different. Are you with me?
But if we are
You can do anything with anything. But as far as I know, Cholesky decomposition way of reducing the rank, as far as I know, there is no theoretical basis to be able to guarantee. In here, I can guarantee, if I pick k to be such and such, I can guarantee I'm 90% right. You can approximate anything with anything. Unless you are able to quantify the quality of approximation, it is not worth the paper written in. You have to develop that. I'm not saying it's not possible, but then ultimately the challenge that you have is that you can use any norm, you can use anything, but you have to say, if I approximate A by B, I lose information, I can quantify the loss of information. That's the key. Are you with me? That's right. You cannot simply throw something out and then I'm approximating. You need to know how much you throw and what is the impact of what you throw on what remains. That's the fundamental. And that's the whole aspect of approximation theory, right? That's right. You had a question on 4D war, right? Is okay? Is good? Good. Now I'm not going to force you to ask questions. But we talked about it, we answered that. How many of you understood the last part of 4D war this morning? How many of you have some lingering doubts of the last part of 4D war? Amit thought that, well, if need be, we can revisit. That's the question. That's the reason I'm using it. You remember, I wanted to avoid matrix multiplication and to replace it by matrix vector multiplication. So we have an expression for the gradient as a sum that involved matrix multiplication. Instead of explicitly evaluating that expression, we wanted to compute that expression recursively. The recursive computation involves only matrix vector calculation. So each loop is only n square. Are you with me? That's right. I don't think there's anything more to that. Go ahead.
Talk not necessarily in a group, but each one of us.
Are you sure you don't have any more?
Somebody has a
Dinner
question.
time, lot more questions came.
Okay, there is.
Okay, go ahead.
In 4D var, you minimize your cost function within the some time window. So that time
It's
window.
called a simulation window.
Yes. So that's time window has some forecast time. Forecast time is there.
Where is the forecast
Means
time?
you give the forecast for suppose 6 hours.
Wait.
Okay.
Sometimes it's the terminology that you use, what I use, and then
Yes.
finding the dictionary between the terminologies.
Yes.
Once I get the right dictionary, then we are on the same page.
Yes.
So 1, 2, 3, 4, 5, x0, x1, x2, x3, x4, x5. I have z0, z1, z2, z3, z4, z5. Okay, go ahead.
Okay. So here you.
So I'm assuming that the assimilation window is 5.
Yes, 5. So after in between we are using somewhere the boundary condition also.
Huh?
Boundary conditions also.
Why are you putting new words? Data is data. Where is boundary condition coming?
But once you assimilate yes.
Go. You are the responsible for what you say.
Yes, yes.
You said boundary condition.
Okay.
Where in the world is boundary condition coming now?
Okay. But when
Boundary condition affects the model.
yes.
Are you with me?
Yes.
The model equation takes care of the boundary condition. Once you fix the model embeds the boundary condition as a part of it.
Okay. But after assimilation at the 5th time step, it will not affect at all the boundary condition.
Not affect what?
Boundary condition at that time.
Okay, let's go back.
Okay.
Okay, I have a model, right?
Yes.
I have, this is xk. In this particular problem, x0 is the initial condition.
Oh, yes.
X0 in some problem, I may have an alpha.
Yes.
The alpha could represent some of the boundary conditions.
Yes.
So if you know the boundary condition is fixed.
Okay.
If you don't know the boundary conditions are control.
Okay. Yes.
Much like you are going to be interested in finding an optimal initial condition, you can pose the problem as one of finding optimal boundary condition also. Are you with me?
Yes.
Okay, so what does it mean? It really doesn't matter what's called control variable.
Okay.
The control variable could be purely initial condition,
Okay.
purely boundary condition,
Yes.
purely parameter, or any combinations thereof.
Okay.
Only for the sake of simplicity and illustration, I assume the control to be initial conditions alone, because I thought of the model as an initial value, forecast of initial value.
Yes.
Are you with me?
Yes, sir. Okay, thank you.
In other words, boundary condition has no separate dealings. Either it is known or it is not known. If it is known, it becomes part of the model description. If it is not known, it becomes part of the model description and also control.
Sorry, I
My question is that suppose if you are changing the initial condition at x equal to x naught.
He said yes to me, and now he said he has a question, right? I don't know what he meant by his oh, he's a good friend. I'm trying to pull his legs. Go ahead.
Okay, I just repeat the question with you. At time equal to suppose 5 hour forecast he gave. So at 5th hour forecast, there is some after data assimilation there is some change in initial condition, and also there will be some changes maybe in the boundary condition also. So that we will take care or not.
Why would you say after 5 hours there is some change in initial condition? Who changes that?
Yeah, because we are assimilating some data at the 5th position also.
One by one. I want to make sure whether I understand him first before I get reinforcement. 1 second. I know.
Because we are assimilating at the each time step.
But you have to state the problem mathematically. Are you with me?
Yes.
Yeah. So how do we state the problem mathematically? I know the model very well. I know. Okay, good.
Okay.
Yeah, that is probably the problem. That's right. That's what I'm coming to.
Okay.
Okay, let's
So that means that two people can't win.
let's hear our friend what he says. Let's hear our friend what he says.
Actually, in continuation to what he was saying, whenever
Oh gosh, this guy has the telepathy. He knows what he says. He is the most powerful man in this room. Absolutely. Go ahead.
actually whenever an analysis is being made, just as he was saying, whenever the analysis or assimilation has been done, that has been done along with the first case observation and the boundary condition. So after assimilation has been done, this nodal boundary condition has to stay. And assimilation taken as the initial.
If you understand it, I have no question. Look at this, he gone from 40 bar to 3 bar now.
It's the similar thing. In 3 bar also we update the boundary condition after the...
Yeah, but then I want you to understand, don't say boundary condition, don't say initial condition, don't say parameter, say control. Are you with me? I'm giving you a broader framework. What is unknown? What is that if we change is going to change the solution? The whole idea is to fit the model to data. If you want to be able to fit the model to data, you should be able to change the solution of the model. All those terms which help you to change the solution of the model are called control variables. In the setup I did this morning, I assumed for simplicity, initial conditions are the only control. It can take any shape or form. Are you with me? If it is boundary condition, so be it. If it is initial condition, so be it. If it is parameter, so be it. If it is a combination, so be it. Okay, go ahead.
Actually, whenever an assimilation is being done, to make it balanced, like in the morning when we were asking about why if nudging is easier to incorporate, why if nudging is easier, then why is people shifting from 3D bar to 4D bar or carbon filter? The main reason was that in nudging technique, the balance between various variables are not taken into consideration.
That's not the question where he's coming from.
Actually, what he is saying is, whenever we are making an assimilation, we are changing this mass and physics balance. Boundary condition is already set up with that with earlier balance.
That is right.
So make it inconsistent with the initial conditions. In like whatever model we run, we have to update the boundary condition so that it is in consistence with the initial condition. So that is done separately.
If that is done, why do you do data assimilation? If you can find an initial, hold on a minute. If you can find an initial condition consistent with everything else, what in the world data assimilation is doing?
I think there is a big...
Okay, good. Go ahead. I still have a gap in my mind.